Okay, so welcome back. So last time we are discussing binary quadratic form. So a binary quadratic form, the idea is to relate it to the class group of imaginary quadratic field. So the basic concepts are the following. A binary quadratic form is a homogeneous polynomial. It's a homogeneous polynomial of degree 2 in two variables. It's of the form ax square plus bxy plus cy square. And in this course, we are only interested in those which are integer. So binary quadratic form is can be written as x transpose ax, where A is a symmetric matrix given by A, b by 2, b by 2, c, and xy is a column vector. And this is said to be positive definite if this matrix is positive definite. So it basically means x transpose ax is positive for uh, all x non-zero. And uh, so binary quadratic form has the discriminant b square minus 4ac, and positive definite means that discriminant delta b square minus 4ac is less than 0, and a and c are both positive actually. So an integer is said to be represented by a binary quadratic form fxy if it is the value of fxy. Then we say that the form is represented by fxy. And uh, yeah, and then this question of SL to Z equivalence. So if there is a SL to Z matrix PQRS, so what is SL to Z? So SL to Z is 2 by 2 matrices with integer coefficient with determinant equal to 1. So if fxy is of the form x transpose ax, where A is ABCD, and if you have g xy, so actually I should write, maybe I should just write b by 2, b by 2, b by 2, b by 2, and c, just to be consistent with them. So they're said to be equivalent. So if the matrix of B is uh, uh, so PQRS, so where PQRS are integer and PS minus QR is 1. So, and this is the transpose of this matrix. So it is of the form some Q transpose AQ, where Q is a SM to Z matrix, 2 by 2 integer matrix of determinant 1. So then there's said to be properly equivalent, the term due to Gauss. And then the corresponding forms looks like this. Yeah, the corresponding form looks like A prime, B prime, C prime, X square. And obviously you can explicitly write down what is A prime, B prime, C prime. Then this proper equivalence was the equivalence relation. And a form is said to be primitive if GCD of ABC is 1. And this proper equivalence maintains primitiveness and keeps the discriminant. So discriminant remains the same, and the primitive form remains primitive, and positive definiteness also is maintained. So if we define a relation that f is equivalent to g, if f and g are properly equivalent or SL to z equivalent, then this is reflexive, symmetric, and transitive, because SL to z set of 2 by 2 matrices forms a group in the sense that inverse of every element is there, and if A and B are in SL to Z, then AB is also in SL to Z. So in this equivalence class, you want to a primitive binary quadratic form is said to be reduced if so you want to basically identify one particular element in equivalence class, and a binary quadratic positive definite, so integral positive definite binary quadratic form is said to be reduced if mod b is less than equal to a, less than equal to c, and if either of the equality holds, that if this stage there is equality or if this stage there is equality, then a then b has to be positive, non-negative. Okay. So example is x square plus y square, x square plus n square, 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 square. and x square plus xy plus ny square, like that. So the main result we discussed last time, that every positive definite, every primitive positive binary quadratic form. So, so every integral, I should say integral. So every integral positive definite binary quadratic form of this discriminant delta is properly equivalent to a reduced form of discriminant delta. Okay, and not only that, there is no two reduced form can be of same discriminant can be equivalent to each other. So every integral positive definite binary quadratic form is properly equivalent to a unique reduced form of discriminant delta. And this proof we saw, I did not prove the uniqueness, but rest of the proof we did. So we'll assume the uniqueness because we are short in time. And then, so the number of equivalence classes of positive definite binary integral quadratic form of a given discriminant delta is finite. Okay. So today we'll prove this, that corollary of this. So I gave you two exercises that um, if they're properly equivalent, they represent the same set of integers. And I asked this question, it appeared during the proof, such things that if x square plus bx plus xy plus cy square and x square minus bxy plus cy square are properly equivalent or not. So the number of equivalence classes of positive definite integral binary quadratic form of a given discriminant is finite. Okay, so the number of these equivalence classes. So we fixed a discriminant delta, and we are considering negative delta is negative, and we are considering binary quadratic forms which are primitive, as which are integral primitive, and so unless it's integral primitive doesn't make sense. So integral primitive positive definite and discriminant having delta, and then the number of such equivalence classes. So each equivalence class contains exactly unique reduced one, and the number of equivalence classes we are saying is finite. Okay, so you look at this, the delta. What is so in this setting we have delta is discriminant 4ac and it is negative. So mod of delta is actually equal to 4ac minus b square, and then this is greater equal to uh, this is greater equal to 4a square minus a square equal to 3a square, right? Because mod b is less than, we may assume. Okay, so we may assume. So, and we may assume that, we may assume that fxy uh, is bx square is cy square is reduced, that is mod b is equal to mod b, and this is equal to c with delta 4ac. So then the mod delta is greater equal to 4ac minus b square, and this is greater equal to 4a square, because c is greater equal to a and this is a positive, and b mod b is less than a, so b square is less than a square, so minus b square is greater than minus a square, so this is greater equal to a square. So this implies that mod so a is less than 0 is equal to a mod delta by 3, right? Or something. So this implies there are only finitely many choices. A. And since mod B is less equal to A, there are finitely many choices. And everything is integer, remember? And so you want and B is less B belongs to square. Finitely many choices. So B versus B, and since for reference delta equal to 4AC minus B square, so fixed. So if there are finitely many choices of so the C equal to delta plus B square, so delta plus B square by 4A as finitely choices. Okay, so there are finitely many choices. Choices. So reduce. Again, that's it. Right, so we can, so that's what we proved, that every equivalence class contains a unique reduced form. So if the, so every form is equivalent to a properly equivalent to reduced form and no to reduced form are properly. So if you can prove the number of reduced form is finite, there are only finitely reduced form with equivalent discriminant, then positive definite reduced form with equivalent discriminant. Primitive. So then we are done, and that's what we did, just using the property. Okay. So this is called the, so note on the set of equivalence classes of positive definite integral primitive positive definite uh, binary coordinate forms of a given discriminant we can define group structure. We can define a group structure, also abelian group structure. These are called Gauss or something, Dirichlet decomposition. So we'll omit this because we have fixed time, cover this. But so this set of equivalence classes, these equivalence classes forms finite abelian group. Finite we just proved, okay? So the goal is to show, goal is there is a bijection from this set of equivalence classes with the ideal class group of q root delta. Okay, so in fact, the group abelian group isomorphism. But we will not do this. Okay, so this will imply that the ideal class group of q delta is fine. Okay, so this is the idea. So you start with a imaginary quadratic field, then you find a delta so that you write it q delta, and delta is a discriminant of binary quadratic form, and then we look at primitive positive technique, such binary quadratic form. The set of equivalence classes is finite, and from there we look at this group is finite. Okay. So I'll write down the map again a little bit. I'll specify, but this group isomorphism we will not discuss. We'll just give it map. We'll show this map is well defined. We'll show this map is injective, and we'll show this map is surjective, and okay. So let me give a quick definition. So let Q root delta be a quadratic field, and delta is in Z. Then delta is said to be a fundamental discriminant for K if delta is a discriminant of the ring of integer. Okay, so recall what was the ring of integer? The ring of integer was this Z 1 plus root delta by 2 if delta was congruent to 1 mod 4, and it was Z root delta by 2 if delta was 2 or 3 mod 4. Um, then a quadratic field Q root delta. Delta is a fundamental discriminant if either delta is square free and delta is 1 mod 4, or delta is so it's called a fundamental discriminant if it is, as I said, the discriminant of the imaginary quadratic, the ring of integers, and the discriminant of the ring of integers. Right, that we have defined. The ring of integers, the discriminant was, it was Z 1 plus root delta by 2. The discriminant was just delta, and if it was root delta, it was Z root D, then the discriminant was 4D if D is 2 or 3 mod 4. So that's why I've written it like this. So for a quadratic field Q root delta, delta is a fundamental discriminant. The way to check it, delta is square free and delta is 1 mod 4, or delta is 4D and D is square free and D is 2 or 3 mod 4. Okay. So in this case, delta is congruent to, so in this case, also recall that O of the ring of integer of root D, root delta, can be written as Z delta plus root delta by 2. So it's one of the exercises I have earlier, if you recall. Okay, so check your notes. I have given this exercise. So again, what do I want to see here? So we have a map. So we have a map from this set to this set. One is the equivalence class of integral positive definite primitive binary quadratic forms of discriminant of given discriminant delta, and the equivalence class of ideals of the ring of integers of Q root T. Okay, so what was the equivalence relation here? Here the equivalence relation was two forms, two integral positive definite primitive binary quadratic form are equivalent if the symmetric material associated with those two forms is given by the matrix of A was some Q transpose AQ, where Q was in SL to Z, right? This is the equivalence relation. And here the equivalence relation was I is equivalent to J. There exists alpha beta in OK, alpha beta not equal to 0, such that fxy was equivalent to gxy if and only if this happened, and here I was equivalent to j, so that alpha I equal to beta, right? This was the properly. So if x was equivalent to beta, if and only if this was x transpose fx, this was x transpose x. Okay. So what is the map? Right, this was the equivalence relation, and so what was the map of this? I should maybe I'll do this. And yeah, okay, so okay, maybe I don't need this right now. Maybe. So what is the map? This was the equivalence relation. Uh, okay, so what is the map? So here you take a binary quadratic form, fxy, ax squared plus bxy plus cy squared, and such that p square minus 4ac equal to delta, and then you send it to this ideal if, the equivalence class of if, which is equal to uh, the ideal generated by this set ZA. I'll explain Z B plus B delta by 2 minus B plus B delta by 2. And here, if you have a form, if you have an ideal I, then it is generated by some alpha and beta. Then you send it to so Z alpha plus Z beta. Okay, and so direct sum, and then you send it to uh, norm of alpha x plus beta y divided by norm y. This is the map. They're inverses of each other. And so we'll just show that this map is a bijection. So we'll start with this map. We'll send it here. We'll show it's well defined. So if f is equivalent to g, then the class of if should be equal to class of if ig. So that is the three steps. So it's equivalent first step. So equivalence classes goes to equivalence classes. So the map is well defined. If f and g are equivalent, then if and ig are the same. The equivalence class of if and ig are the same. So this map is well defined. We'll show this map is injective, and we'll show this map is surjective. And as I said, what we'll not do on the left side, there is a group structure, abelian group structure, and that abelian group structure carries it isomorphically to this abelian group. Okay, so that part we'll not do. So we'll show these three steps. So three steps. Okay, so this is the map and three steps. Three steps. Well-definedness, injective, and subjective. Okay, so let's start. What is the map exactly? So the map is fxy equal to ax square plus bxy plus cy square, and you send it to. So we are starting with positive definite. So integral, primitive. I'll not write it again and again. Primitive and positive definite, definite binary quadratic form fxy equal to x square plus bxy plus cy square, and then delta is b square minus 4ac, and we know delta is less than 0. So root delta is an imaginary number, imaginary complex number. So you send it to m times this set ma plus n times minus b plus root delta 2, where m and n set. Okay. Note that in this case, as I said, O delta is Z root delta plus root delta by 2, because we have delta as a fundamental discriminant. So mm, we are considering delta is b square minus 4ac. So and we are considering q equal to. So what is our imaginary quadratic field? So q equal to. Sorry, we are considering q root delta. Okay. And because delta is b square minus 4ac less than 0, and delta is congruent to. So O delta in this case can be written as delta plus root delta by 2, and so it is equal to m plus some, or I don't know, how can I say r plus s into delta plus root delta by 2, where r is inside. Okay. So notice that delta plus root delta by 2 is b square minus 4ac plus root delta by 2. So it is minus b plus 2m by root delta. I can write it as minus b plus 2m by root delta by 2. So minus b plus root delta by 2 plus m in z. So basically I'm saying the ring of integer can be also represented by see b square minus 4ac. If minus 4ac is even, so I can write it as minus b plus 2m plus root delta by 2. So it is minus b plus root delta by 2 plus m, right? So OD, which was Z delta plus this set, if I call this something equation number 2, then this set is same as uh, this set minus b plus root delta by 2. So in particular, if I define for f, omega f is minus b plus root delta by 2, then omega f, this belongs to this in the ring of integers, right? And and if is if is O delta, which is Z omega f in this notation. Okay, so at least it's inside the ring of integers. So what we are doing here, probably I should clarify. I am starting with q root delta. Okay, an imaginary quadratic field, and I'm choosing delta to be the fundamental discriminant. Okay, so okay, so so delta is either 1 mod 4, or delta is 4 times d, or d is square free, and d is 2 or 3 mod 4. So I can write my imaginary quadratic field is q root delta. Then I am looking at this positive integral imaginary quadratic form with the discriminant equal to that same delta. Okay. And then I'm saying that the ring of integer with this choice is delta plus root delta by 2. And then, so first I'm starting with imaginary quadratic field with fundamental discriminant root delta, with fundamental discriminant delta, and then I'm looking at binary quadratic form of that discriminant. I'm giving this map, and so ring of integer is this, and I'm choosing this element Z, Z abelian group generated by A and minus B plus root delta by 2. So what I showed, you look at minus B plus root delta by 2, then this is in the ring of integers because delta plus root delta by 2 is minus B plus root, and minus B plus root delta by 2, they differ by integer. So some integer, differ by some integer. So this is in the ring of integer. And because they differ by integer, in fact, the ring of integer can be generated by this also, minus b plus root delta by 2. So given an f, you define this minus b plus f was ax square plus bx, bxy plus cy square, and delta was b square minus 4ac. So you decide omega, you define omega f to be this, then O delta is z omega f. Uh, because of this, you can easily check it is. So IF is at least inside this. So what we have to show, first of all, is IF an ideal, right? So we are giving this map to an ideal. So to show it's an ideal, it is defined as a Z linear combination of two elements. One is A and B plus uh, minus B plus root delta by 2, which we are calling omega f. So Z omega f is itself the ring of integer. To show it is an ideal, what do you have to show? You have to show that Z omega f times this IF is contained inside I. That's what you have to show. It's already an abelian group because it's a Z linear combination of two elements. And this is your, because this is your ring of integers, so you have to show, so you have to actually show that OD times this, O delta times this is contained inside this, but this is equal to, as this small calculation, so is B plus root delta by 2. So you have to show this times, which is Z omega F. So you have to show Z omega F times IF is contained inside I. So that basically turns out to showing that omega f times if is contained in I. Again, by definition of if, it is a Z linear combination of an integer element A and this omega f. So it's enough to show omega f times omega f inside I by the definition. Okay, so these are some reduction. So it reduces to show omega f times omega f is contained in if. And next time we'll do that, and that will show that if is an ideal. So this map will make sense, and then we'll show that why this map is well defined. So, and then we'll show why it is injective and what is subjective. So we started with an imaginary quadratic field with fundamental discriminant. We wrote SQ root delta, and then we found it. Looked at a binary quadratic form with the discriminant, and then we gave this map, or we suggested this map. So we'll check it's well defined, it's injective and such.